you won't be able to hear the video audio on this because it's not HDMI, it's the 15-pin connection today for some reason. The benefit, I guess, is that it fits on the whole screen rather than being kind of off to one side, which it does on the widescreen with HDMI. So anyway, maybe not important for our discussions today. So we're getting close to the witching hour. Watch some videos first, maybe take care of some house cleaning business about the midterm, etc., just briefly, and then talk about fluid dynamics now, which we really are involved in now rather than fluid statics, as we kind of move this along. Fluid dynamics, of course, is fluids that aren't sitting in a bucket and not circulating, but are circulating. And of course here, this is what the America's Cup looks like these days. They used to be regular sailboats. 27 meters was their the class, I guess, 27 point some meters. I don't think that was ever the length of them, but it was some combination of different lengths of the beam and the draft and the length and the sail area somehow that came up to some formula. And they used to be monohulls, and now clearly they're not. And obviously, in terms of fluid dynamics here, sails catch the wind. These multi-hulls lift out of the water. They have basically airfoils, which is exactly the same as a plane's wing and serves the same function, that lifts the boat out of the water to be able to reduce drag. And so are just actually amazing boats when you look at it. And these guys working on the, I think they're generating power, right, to run winches and things. Presumably that's exactly what they're doing. So just actually amazing boats. I think they go 50 miles an hour or something. And I can't remember where this, I always thought this was the Bay Area, but I think it's Bermuda, actually. I was just looking at the title of this. And so these used to be, and clearly these are using in some way fluid mechanics to do the aerodynamics, both of the sail and of the boat. I made you watch our New Zealand stuff from on your first Labor Day stuff online, and so this is the New Zealand America's Cup challenging boat from a few years ago now. That has a specific hull in it. I guess there was a big furore. You saw it actually on the second day of class when we talked about fluid mechanics in recreation, etc. You saw this winged keel on a boat, which was the innovation that the Australians had, that they used to bring it to the water every day in Newport. America's Cup, I think, has always been challenged for the last many decades in Newport. And this Australian boat beat them by this innovative design on the keel, which they didn't want to share with anybody. And so they had it shrouded. And so clearly boating is one of the features of what we could look at. Kind of related to what we'll do as well. With a bit of jackass here. Not so much today, but we'll talk about not just clearly this fluid mechanics problem, something squirting out of a hose on this rodeo hose. And we'll look at what flow rates do you need to be able to get stuff to be able to hold a person on it. We'll analyze this many times as well.
This is what $128,000 US
toy. I'll shut off the sound just so it doesn't overprint me. We wouldn't want that. But it's some toy, I don't know, $100,000 or so. An umbilical that tows a pump in an enclosure that squirts water under pressure out of these two nozzles, and you throttle it like a motorcycle to be able to lift yourself off the ground. And I think one of the videos we'll look at is that this made the crossing between LA and Catalina Island, one of the islands offshore California, which is not an inconsequential trip. And we'll also, maybe at the end of today, if we get to it, we'll do the analysis of this, which again is an indication of, if you're lifting this heavier than airplane off the ground, then you need to be able to provide some motive power to be able to do that. And of course the motive power is in the thrust from the engines, which allows you to trundle down the runway maybe to a couple of 100 miles an hour, 150 miles an hour before you take off. And this is a kind of a public safety video that we'll switch to this in a second, looking at towing in this case, I guess basically giving a warning not to drive behind a jet when it's getting to go and do something. And so this is, I'm pretty sure this is San Francisco International, just from what it looks like, one of United hubs. This is an old movie, you can tell by the livery on the plane. It's not modern livery. And also by the model of the truck. I guess you probably wouldn't use a 2019 truck to do this, but it clearly is an older model, and perhaps a junker that they didn't feel too bad about blowing off into the water, as it turns out, ultimately. I presume they dragged it out. And so again, that's the kind of problem that we might like to solve. So now we're talking about fluid pressures on something. We can resolve the forces just as we have in statics, but now the forces aren't due to a static fluid, but they're due to a fluid which is moving. And actually, as we go through this, we'll learn that really fluid dynamics is not really much different than if you threw a baseball at me and hit me in the chest. Not that you want to do that, of course. The transfer of momentum from that moving thing to me is not very different from water doing it once for one packet of water and then following that for the other packets of water if you're squirting something with a fire hose. And of course the jet engine is something that's a bit like that as well, because it's just not a fire hose, but it's a stream of air that's coming out of the system. Okay, so that's what we'll start talking about today. I see from my email, you should see from your email that I sent you something last night in terms of one of the announcements. This is it here. And so maybe just talk about that briefly. So a week today in the evening, next Wednesday in 121 Sparks, which conveniently is just upstairs from us, is your first midterm. All the stuff to prepare for it is online, and also some suggestions of exactly what's on the test in terms of both the scope of the class, I guess, the scope of the potential material. It covers up to 4.1, which is Monday, and those topics. But the questions are limited to these topics here. And so that allows you maybe to focus your planning, I guess, and preparation for it. You can bring to the test a calculator, pencil, ruler, etc., and an equation sheet back and front, anything you like on it, handwritten, typed. I'm not sure we need to take them in. Sometimes we've taken them out. Yeah, you can put whatever you like on it, and it's stated here. 90-minute test, 8 till 9:30, but the room will be open to midnight, as you wish, so you can do your best work. Online, and this should be a link to it, I think. Online is a recording. 26 views I see down here. And so that starts off, and so you can listen through this. And my guess is that on this recording, this brief recording for 27 minutes, it covers every equation that you'll need, but you need to know how to use it. And so that's the deal for this class, is knowing how to use it. So you can use that. I used to, in the past, record a much more comprehensive review session. So if we look on here where the reviews are, I'm guessing that the 2013 one probably covers all the material from 1.1 to 4.1. And so if you want the big picture, then go earlier, and I think these review sessions are quite comprehensive because this one runs for, I can't see it, if it runs 57 minutes, I think, and it's probably recorded in class. And so that's available to you if you want to use it. It's up to you. But probably having you focused on what you physically need for this allows you to at least concentrate on the things that are important. And you can see from the questions, the fluid pressures on structures, I think part is buoyancy and part is a viscosity. So that's it. So, any questions for clarification on anything? No? Necessary part, I think, of the class. It's an assessment to see exactly how you're absorbing the material. And so, to me, I think the best way to prepare is, as I said before on the first day we met, is to have a look at the past exams. If you can ace the past exams, especially in the areas that that you're pointed to now, then I think you can walk in and do a good job on it. And as I said before, it's great if you can do a good job on this first one, because that sets you up. It gives you a buffer. The scoring for this whole course ultimately becomes, I think, 114 points, of which full score is 100 points. And so between the quizzes and the extra credit for the exams, which is 10% extra, so it's a 300-point exam, but it's out of 330. Top score is 330. There is no curve, but if the top scorer gets less than 330, then we boost everyone's scores up by that amount. Typically, it's not very much. It's either 0 or 5 or 10 points out of 300, maybe. But that's what we end up doing. So anyway, so that everything is crystal clear, that you know what the deal is. So use the. I don't know whether you've been using the TA. We have a TA for this class. I'm guessing if it's anything like last year, that his services haven't been used very much. I haven't seen very many people, almost none. I'm not sure Jihao has either, but use the resources available to you. Okay. And there's lots of resources online. It's actually quite a convenient way to do it, I think, these days, to be able to do that. All right? Questions? All right, fine. Yeah, it's never a pleasant thing to have to discuss assessments, quote unquote, but somewhat necessary. Yeah, okay, and so you know the schedule. All right, so we're going into a new regime, if you like, now, in terms of, we've talked about fluid statics. Now we're talking about fluid dynamics. And so in terms of what we might want to talk about, all right, so, yeah, all right, so, well, typically, just a very, very quick recap. You know that in our discussions, we've talked about the cases where we have either accelerating or non-accelerating fluids. We've relaxed this to the fact that these are accelerating. And if we do that, we get a couple of standard results. One is that in a bucket that either is moving horizontally with some acceleration, we can get either the slope of that surface and we can also get the pressure distribution that results from that as a standard result. And that pressure distribution is something like P0 plus a depth from the surface multiplied by gravity plus a vertical acceleration times the density of the fluid. This is the second final result that we had. So we had one for linear accelerations, which was this and this, and we had one for centrifugal or rotational accelerations, which is rotating around some kind of axis with a center line in it, which we suggested had some shape like this, and we could get the elevation of this free surface, which would give us the Z location, and we could get some pressure distribution along the bottom of this that would vary in some way, and that was given by this. So those are the two standard results. And so you've probably already seen that that doesn't seem to be one of the questions that you have on your roster for a week from now. So you have a look at the material if you want to reevaluate that. But the important feature from this, I think, is that at least in looking at these rotational behaviors, what we did was we looked at this little video online, and we looked at this idea that we might have a block that was rotating, that was moving around in this direction, theta, and was being pulled in some angle which was theta, and depending on the radius of this lever arm, there was some force that we had to apply to it, right? So we could swing this thing around. Could be a weight on a string. We know that there's a tension in the string to keep it accelerating. The speed's not changing because it's going at constant rate, but the direction is changing every increment as it goes around, and we have to provide a force to be able to do that. And so in the same way that we looked both at linear accelerations and rotational accelerations, then when we look at the behavior, for instance, of an airfoil, try and draw this. I'm not sure whether it's a very good airfoil. It's not a very good airfoil, but it gets the point over. Then if we look at the behavior of fluids which are now moving, so in other words, obviously, if you're swinging a piece of rock around on a string, it's moving. But if that rock is a piece of water that's contained within this flask, then it's really not circulating. It's setting up a static configuration and not moving. But now we're talking about systems where the material is moving. And so if you think about it, the essence of what we're going to talk about now is being able to write the behavior as we go from one location to another location along a streamline. And what we'd like to be able to do is say something about how the fluid pressure changes as we go from location to location along a streamline. So it might be that we're going at some velocity here, which would be v1, and it might be that we're going at some other velocity v2 here along the streamline. It's basically a linear system, but it could be that the velocities are different. If the velocities are different, it means it has to have accelerated from one to the other, which is why there's an analogy with linear acceleration. But you can also imagine that going around this hump here, it's not so different from being attached, the fluid being attached here with some kind of radius and being flung in this direction as well. And so in our discussion of Bernoulli and fluid dynamics, if you like, we'll do two things. We'll look at behavior along a streamline, which is in this case really going from point 1 to point 2, and it's directly analogous to this behavior here. And we'll look at going across a streamline, and that behavior might be going from this point here, say point 3, to point 4. So in other words, it's perpendicular to the streamline, and we'd like to know how the pressure distribution changes. We know that if that was vertical, and you go vertically down from that point, then the pressure distribution will just be the weight of the fluid, kind of this linear increase in pressure as you go down. But what happens if it has a curvature to it? You can probably guess. It's like going over a roller coaster. As you go over a roller coaster, you feel lighter than you would be, because gravity acting on you is reduced by the centripetal force, and therefore you feel lighter. And so you could imagine that distribution of fluid pressures, instead of being the static distribution in water, this linear distribution, is actually reduced. Likewise, if you go into a well, driving on a bumpy road, you go into a dip, you get pushed into your seat, you could imagine also that the fluid pressures that act are increased, just like going up or down in an elevator. So they're directly analogous to that. So what we'd like to use in this is we will use Bernoulli. So you've probably all seen Bernoulli in your plast. Daniel Bernoulli. And what we might do is start from at least something that we know, and that is that we've talked about being able to calculate fluid pressures, for instance. I guess this is all on the screen, at two different points. And if we looked at the equations that we used to do that, they looked something like, what did I want to start? Yeah. change in pressure with elevation, z being upwards, plus density times gravity. Sorry, not plus. I guess it is actually in this form. Both are minus. Minus density times the acceleration in the z direction is equal to 0. The analogy we had with this was that this is the same as force minus mass times acceleration is equal to 0. Newton's second law. And that in this, what we could do is we could take out this acceleration in the z direction, and we could merely write it as a change in velocity with time, which we could multiply by 1. And if we do that, then we end up with these two terms here. So we'd end up with change in location with time is just a velocity. Change in velocity with location is a term that we have, which is really just the acceleration, not in terms of time. So if you're attached to something and you know that at one time you're doing this velocity and another time you're doing another velocity, then this dv dt says what your acceleration is. If you're a static observer and you see something going at some velocity here, and later you see it, the same packet of fluid going at some different velocity, then it means that it's changed velocity as it's gone from one location to another, if z is the direction along the streamline. And so what we can do is we can substitute this as a standard result, and this ends up being a half d dz v squared, which you can differentiate by parts just to confirm that this is that. And so if we resubstitute these terms back into this expression, into Bernoulli, we end up with, I guess we can get rid of the negatives. We don't, because it's equal to 0. We end up with change in, let's make them actual derivatives. We have dp dz plus rho g plus density multiplied by this term here, which is a half dz v squared, which is equal to 0. And so what we could do, I suppose, is we could multiply by dz. Didn't leave myself much space, but there it is. And if that's the case, then we get rid of these. We get rid of these. And I suppose we could also integrate what's left without rewriting this multiple times. And if we do that, then the integral of dp is pressure plus the integral of density, not very good density, gravity, and this is the integral, right? Plus the integral of this is just density times a half v squared. And instead of being equal to 0, it's equal to a constant. We could integrate between limits, or we could just integrate and you end up with a constant you have to figure out. And if we divide both sides by rho g, all sides I guess, all terms by rho g, then voila, you end up with a relationship which is pressure divided by unit weight plus elevation plus hopefully a half v squared over 2g. I'll just write it as that, or v squared over 2g, which is constant. And if you know anything, you remember anything about Bernoulli from your physics classes here or your high school physics classes, is that typically we write it between 2 points. And so if we can write this equation at point 1, then this would have these appropriate subscripts. And we can write it as being equal to point 2, in which case the subscripts for this would be here. And we should be able to then equate those behaviors at those 2 points. And so what we're interested in doing is merely being able to evaluate it at 2 different points, an upstream location and a downstream location. It means that we will have 6 quantities in this equation, and so we hope that we know 5 of them to be able to solve directly for that last one. If we only know 4 of them, then we can do some tricks with conservation of momentum, mass, to be able to solve it. In other words, mass in equals mass out, which we'll deal with in due course. But that's the essentials of what we'll attempt to do. So that's Bernoulli. So we could have derived Bernoulli using very long derivation that's here, that goes on forever, that isn't much fun, but I think we're already at that point. So what are the constraints on Bernoulli as we look at it? Well, actually we can use it in a huge number of instances. All of the things that we looked at in the little videos as we rolled into this, we could use Bernoulli, even though it's limited to certain conditions. And so these certain conditions are these 4 values here. So it's typically for incompressible fluids, but we always use it for air. Air is a compressible fluid, it's a gas. And typically, so long as the velocities are not so high, then and the pressure differences are not so large that compressibility gives you different densities at different locations, then it works just fine. In fact, we'll do this the airplane example today just to look at how that works and whether that makes sense for us. It's for irrotational fluids. So in other words, as it goes downstream, we've used this example of a airfoil. Maybe not drawn so well. And we've looked at these streamlines. So important to note is that the velocities that we're talking about at points 2 and point 1 are streamline velocities. So the velocities in the direction of the streamline, always. And it's useful to get in the habit of writing things between upstream and downstream in this order. There are always velocities in the streamline. It doesn't matter for what we do now, but when we talk about energy losses within the system, then that's a key issue for the way that we write our equations. So what it's not accommodating, I suppose, is that we can't allow it that this flow is doing this. So you're getting these vortices forming in here. So irrotational means that it's just a laminar flow. When we talked about viscous behavior, we talked about this idea that if you take a deck of cards and you shear it, that's really the viscous behavior you're talking about. And so that is that every little platelet of fluid is moving parallel to its friend both above it and below it. And clearly that's not really the case when you get these squiggles, these vortices that are forming. So it has to be incompressible, but that's not a very strict limit. It has to be irrotational, so we can't look very easily at vortices. The flow has to be steady. So steady state flow means that it's not changing. So certainly the velocity here may be different from the velocity here, but what steady flow means for us is that if we take a photograph of this flow regime with all the velocities defined at every point at time 0, and we come back 10 seconds later, or 10 minutes later, or 2 days later, then the flow patterns are exactly the same. They haven't changed. So if your plane's trundling down the runway at 150 miles an hour getting ready to take off, and the airflow is going across it, and if you were sitting in the plane, and that's an important thing, if you're looking at the plane as a static bystander, then the wing is here at one moment, then it's here, then it's here, then it's here. Clearly that's not static in the frame of reference that you're using. But if you're sitting on the plane, or attached to the plane, and you're looking at the flow around the wing, then you could think of yourself as going at 0 miles an hour, and the flow across, and the flow direction, the mean flow direction on the wing, geez, sometimes it goes crazy, and the direction of the mean flow on the wing is 200 miles an hour, or probably 150 as you take off, I'm not really sure, right? And so it's only steady if you choose the right frame of reference. The wing going from here to here to here to a static observer is not steady, but looking at it in this context is, so that has to be one thing. And it's inviscid. So inviscid means that the viscosity is 0. And so there's no frictional losses. In liquids, we talked about the viscosities of fluid. The viscosity of water is 10 to the minus 3 Pascal seconds. Doesn't matter. It's 2 orders of magnitude higher than air. And so clearly, water has some viscosity. But actually, Bernoulli equation tends to work out quite well for most of the liquids that we'll deal with. It actually does remarkably well for these constraints that we have. And so in your classes, environmental systems engineers and mining engineers, petroleum engineers, certainly energy engineers as well, in looking at these flows and in looking at porous medium flows, where fluids go through porous media, then that's also Bernoulli. You can allow for Bernoulli, but you just throw away this velocity term. So porous media flows are so slow that this term is so small compared to the others that you just throw it away. But you need to accommodate viscous losses, and those viscous losses are embodied in what you'd call permeability or hydraulic conductivity. The other thing that perhaps is worthwhile mentioning while we're here, clearly we talked about dimensional homogeneity. The units of Bernoulli have to be in units of length, and so each of these terms also have to be in units of length as well. And so certainly now you're in a position to be able to make that check, to be able to check those units should you so want. Okay? So we don't need to do these derivations because we're already there. We have Bernoulli, we've gone through this, and we've got to this final point here. And so how we'll use it is to realize that if we can define a streamline that we think is the proper streamline through a system, then we can write Bernoulli along that streamline, realize that it's constant, and if it's constant, then we can define it in terms of 2 points. Maybe the behavior at the upstream location and the behavior at the downstream location. And so a pictorial, graphical description, I think, of Bernoulli is embodied in this. This is referred to as the energy grade line. And I suppose the statement of Bernoulli is saying that upstream and downstream, the energy is the same in this water that's moving. It's just that it's different types of energy, potential, kinetic, and force, are partitioned in different ways. And so the fact that this grade line is horizontal so long as viscosity is 0, viscosity being 0 means that if you drag something across a fluid lubricated surface, there's no resistance to my hand being done that. So in other words, there's no resistance to it moving. It's frictionless. And so that means that there's no loss as I pull my hand across here. So that's why the energy grade line is constant, because it doesn't lose energy from being upstream to downstream, it just substitutes it. We can also define something else in here, which would be called the hydraulic grade line. Sometimes HGL, as you can imagine. So EGL and HGL. And the only difference is that I can't do, that's inconvenient. These 3 terms are part of EGL, but the hydraulic grade line is just the sum of these 2. And sometimes that's useful. It's useful in groundwater hydrology because we don't care about these velocity terms, they're 0. And so if you look at writing Bernoulli at this point, then we choose a datum where the elevation is 0. We have to still remember that we always write our coordinate system with positive z vertically, upwards. And if we do that, then we can look at the behavior at a single point. So this point here has an elevation z1. If we looked at the pressure distribution below this free surface, you'll have to take it on trust from me, but it would look something like this. The linear distribution we're talking about. We're really only interested in the fact that the pressure here is this magnitude here. And so this magnitude here is a length, and that length is equal to pressure over unit weight. I always use unit weight for this. It's more compact. And that the velocity of this is given by some height to this imaginary energy grade line, which is given by the velocity at this point here, divided by squared and divided by gravity on the tangent bar. And so the sum of these three things represents the total energy per unit volume, if you like, at this location. And if you go downstream to point 2, then it's partitioned in slightly different ways. Now, this is kind of a representation of a hydraulic jump, a weir. So fast-moving fluid, it goes through some transition that gives it some change in elevation of the surface as you go down from one point to another. If you go down now, you can use this to be able to define the individual terms. The elevation has changed if you look at the pressure here, and the sum of these two components, presumably this would be the pressure. Not presumably, this would be the pressure. And it would be the pressure at point 2, and this would be the new velocity, which is here. And so you see that the velocity at point 2 has to have increased because these two lengths are different from each other. And you could surmise that because the fluid flow, certainly the fluid flow at the upstream, the volume flow rate per unit time has to be the same as downstream because we've said it has to be steady state. So the volumetric flow rate across here has to be the same as the volumetric flow rate across here. But since the velocity is equal to the volumetric flow rate over the area, and the velocity at this point is equal to the volumetric flow rate over the area, meters cubed per second, meters squared gives a velocity. Since Q1 and Q2 have to be the same, area 2 is less, so velocity has to be bigger. And so if velocity has to be bigger, then that's accommodated by this term here. And so hopefully it makes some sense in that. What we could do is instead of writing behavior between points 1 and 2, we could write them between 1, and we could call this point number 2. I don't know why it's doing that. So this could be point number 2. And we could write Bernoulli to represent that. But clearly here, this is something different. This is a pitot tube. This is this tube that we showed that if you get onto an airliner, you'll see it coming out of the cockpit, pointing forwards. You usually board on the left-hand side of a plane, I guess, for some reason. And I guess so you can standardize the docking arrangements at the airport. So it's this little thing that has a hole in it that measures the destruction of the velocity of air against it and uses the pressure to be able to index the velocity the plane is traveling at. And so typically you can think of this for steady state is that you're static, the pitot tube is attached to you, and the air is flowing past you. And so the consequence of that here would be that the velocity at this point 2 would be equal to 0. And if that is the case, then this magnitude of pressure would actually be augmented by that amount. And so it would turn out that the pressure at that point would probably be equal to this full amount here. P2 over gamma is equal to this full length because V2 is 0. You've destroyed all the velocity. And it's no different from you throwing a brick at me, hitting me in the chest. I destroy the momentum of that brick, and it puts a force or a pressure on me. And that's exactly what it's doing here. So that's the way that we'll think about this. A straightforward example, I guess, is to look at a Bernoulli equation in this. And so we can look at these multiple terms. So we can look at the terms which are elevation, the pressure head, and the velocity squared over 2g terms. And we can look at these three different locations. Point 1, which is here. Point 2, which is here, coming out of the nozzle. And point 3, which is here. And so if you look at these and look at what these values signify, so here the elevation is small, it's low, but presumably the pressure inside here is high because you're compressing it as a syringe. Something's driving the flow. And the velocity probably is not very much. It has some velocity, right, because the plunger is moving up, and the fluid presumably has to be moving up with that plunger. And so the velocity isn't 0, but it's probably not very large. When it squirts out of here, all of a sudden it issues out of the tip of this thing. The pressure it feels against it horizontally, because it's atmospheric, has to be atmospheric. And so the pressure it feels now is low, because it's no longer under pressure. It's released that pressure. The elevation, I suppose, is moderate, because it's higher than it was before. But what it has gained is it's gained a lot of velocity because it's being squeezed out and being squeezed through a small orifice. And so this volume rate of flow, which is the same on this surface as it is here, is amplified by the fact that it's squeezed out of a small hole. And finally, when it reaches its peak, its zenith, and then can't go any further and falls down, then all of a sudden the velocity has to be 0. So I guess it's 0, it's gone down to 0. The elevation is at its maximum, and the pressure also is kind of neutral, so it's atmospheric. This is also atmospheric. So I don't know whether this should be a straight line or it's not negative atmospheric, but it's the same here. It's the same at both these equations. So this is just the idea. I suppose if you wanted to, I've never done this before, but we could draw an energy grade line which described those behaviors along this thing. This would be the EGL. And we'd see that each one of these portions was different. And so this one here, this would be almost entirely equal to the elevation, no velocity and no pressure. This one here would be equal to a small elevation, 0 pressure, but lots of velocity. And this one here would be equal to almost not very much elevation, depending on where we take our location. A big pressure, actually almost all pressure, right? Just leave the velocity out. P over gamma. And V, not very big. So actually, yeah, that's quite good. So this is just this energy grade line flipped on its side. And so we can do that. All right, so that's exactly what Bernoulli does. Let's just close out. We have probably some time. I know I'm taking it off very quickly, but you can look at the movie later. I always like doing this one example that we looked at for SFO, just because it's pretty straightforward. And so you remember we had this nice jet engine, and we had a truck which I won't draw very well, but what's it look like? And we have a streamline that comes out of here, hits the truck, and it goes either side. Goes both ways, but let's assume that it just goes one way. And so what we could do is we could write the behavior at two locations in terms of Bernoulli, which is this equation here. Between an upstream location, which is this jet engine, and a downstream location. And figure out what we know. Well, certainly in terms of the coordinate system, this elevation here and this elevation are the same, so we can cancel those. The pressure as it comes out of the jet engine is no different from the pressure coming out of the syringe. Horizontally acting on the jet has to be 0. Pressures in all directions have to be the same, and therefore the pressure here has to be atmospheric. We're going to take it where it hits the truck and it's being stopped, and so we're not going to put this as at atmospheric. We're going to figure out exactly what this pressure is, because we want to know what the force is on this truck. And I suppose we know that the velocity at 1 is equal to, I said, 200 miles an hour, just because a plane takes off at something like that speed. So we know this. And we know at point 2, if the velocity goes to 0, then this term here is 0 also. So the only terms we have is that P1 over rho g is equal, sorry, not so, right? V1 squared over 2g is equal to P2 over rho g. We want to rearrange that for the pressure, which is equal to, I suppose we can multiply both sides by rho. So P2 is equal to rho V1 squared over 2. And so if we calculate what that is, this is equal to about 100 meters a second. It's a factor of 2 when you convert. So this is equal to 1 kilogram meters cubed is roughly the density of air. The velocity is 100 meters a second squared, divided by 2, which should be something like, what is it? So 100 squared is 10,000, so 10 to the 4 over 2, which is 0.5 times 10 to the 4. And it has to be in newtons per meter squared if you do the conversion. So this is 5,000 kPa, kilonewtons per meters squared, kPa. And so if we want to be able to figure out whether the truck gets blown over, the simplest free body diagram I can think of would be pressure times area, is P2. The weight of the truck around this point here, L1, no, L2 I guess, and this would be L1, right? So presumably we could write a force balance which is equal to pressure times area, which is a force, multiplied by a lever arm L1, is equal to the weight of a truck multiplied by the lever arm 2. I would say these, for a truck, let's make life easy for ourselves. Let's make this 1 meter. Let's make this about 1 meter as well, right? Half of the width of a truck, 6 feet, that's about right. So if that's the case, both L1 and L2 drop out, and we end up with this. The pressure multiplied by this is 5 kilonewtons. The area is 1 meter by 3 meters long, right? 10 feet long for a truck for the side. So this is 3 meters squared. And if you do that math, it's something like 15 kilonewtons. So if you apply a force of 15 kilonewtons, which is what gets applied by this 200-mile-an-hour jet, then the truck that you can push over weighs 15 kilonewtons. And a Ford F-150, looked like a heavier truck than that, is 3,000 kilograms, which is about 30 kilonewtons. So, order of magnitude. So, at least in the ballpark. So that's it. So, 6 variables. We hope that we know 5 of them, so we can calculate the one remaining one, which is the pressure. And if we can do that, then we've got it solved. Okay? So that's it. So, next time we'll continue along with this, looking at flow perpendicular to streamlines, and then we'll carry on with it from there.